Hi everyone. So my name is Sergio Marquez. I'm a senior field application with OneSpin Solutions. Okay, so you don't have these slides in your handout, but they will be in the OneSpin website and in the TBS website, I believe. I'm a technical guy, but I kindly agreed to have a marketing slide. So OneSpin has been, the core technology was developed in Siemens, then incubated in Infineon, and at some point there was a spin-off, but basically what the point I want to make is a very mature technology, and we have actually people in this room that has been using this technology for 13 years, because we started before 2004, and I've seen also all the improvements that have come along to all this time. It's a very successful company. I mean, we saw already in the first slide from Mentor, I think, that the formal verification market is growing, and we are also benefiting from that growing. So a little overview on the OneSpin offering. So we have a whole bunch of automated solutions. Other companies call them apps for X verification, SOC connectivity, and lots of other things. And this is actually, I can confirm that this is also a strong driver of the growth of formal. So we saw this in the Mentor slides, and also with Jasper. And I can confirm that we also have a lot of customers using apps, that basically allow people with very little, no formal knowledge, designers, to harness lots of benefits from formal. We also have a lot of offering in the, let's say, more targeting verification engineers, where you want to write assertions, and you also want to collect coverage on this assertion. So we have a coverage collection which looks very similar actually to the simulation coverage, where we have statement branch coverage. We can export this in XML format so that you can use, merge this with your simulation results. And there are lots of interesting features. For instance, you have assertions, and you have obviously assumption and constraints, and the tool will point out if there is code that is dead because it's dead, but in a different way will point out if there is code that is dead because of your assertions. If you have constraints, assumption, then you can think, wow, why am I not exercising this piece of code? And then maybe it turns out that there is a mistake and over-constraining. So a lot of things here. And then we have also FPGA and ASIC equivalency checking. We are leader in the FPGA market for equivalency checking. And we have strong equivalency checking sequential technology. And really what enables us to provide this strong offering here is also our underlying technology, which is common to all of our products that can handle complex SOCs. Okay. So I'm going to dive now into a use case that I hope you will find at least half as interesting that I found. And it's about an application of at the Renesas. So I want to actually thank our customer Renesas and our team in Japan for coming up with this and sharing this with us. So Renesas uses a platform-based design approach, and basically they have a base product, and then they derive lots of different variations of these products, changing some IPs, changing parameters within the IPs, changing also the connection infrastructure, and basically they want to, the whole point of this is that they want to spin different variations very, very quickly. And they had a very good solution on the design side. So you see, this is the base product, and there are lots of different, there are more. This is just, yeah, how do they do this? So this is just a generic picture where, they can change bus bridges, they can change interrupt factors, they can select different port and packages, obviously different memory sizes, and they create a different variation of the product. So there are several challenges. So on the verification of the IP itself, obviously you need to have a strong verification because you need to verify the IP for different parameters. This is going to be reused a lot, so you need to have high quality verification. On the SoC integration side, when you then put this thing together, there is things that you already, there are apps for this to do logical connectivity check. And, but then, they had to do a lot of simulation-based testing to verify different scenarios depending on the specific variation of the product. And they weren't really happy with the amount of time they had to spend on that. It was quite time-consuming. They had to adjust their test bench. They had to write different tests. So when they put together when they developed, let's say, they put these IPs into their library from when the things are picked, they also come along with some assertions that they have developed. They have done some formal verification at the IP level, so they ship this along the IP. Obviously, you have a different instantiation of the IP with different parameters. You can reuse this assertion to verify the new, let's say, version of the IP for the specific parameters you've used. And this is great. Now, these assertions that they wrote are written in a style that it's a OneSpin operational assertion style. And this operational assertion style is based on a SPA library, so it's fully standard SPA, that enable users to effectively kind of translate timing diagrams into easy assertion at the interface level. So interface level assertions, and these assertions are more readable, and they're higher level, and they cover a lot of functionality within the IP because they are kind of end-to-end assertions. And this is very good for verifying the part of the specific IP that you're looking at. So good so far? Yeah, you with me? Okay, so now when they ship, as I said, this IP into this IP library, they ship along with these assertions. And then, there's someone building up the system, the SoC. Now, you might be, for instance, aware of some apps that we also have an app for this for connectivity check, where you check your connectivity, between your various IP. This is merely a logical check, a wiring check, pretty much. And this, there are a number of companies offering this, including us. But then there's a question: what about functional connectivity? Can I be sure that if one IP is raising, an interrupt request, this interrupt will be correctly accepted by the CPU, even if the other IPs are doing something, there's other things going on? Functional connectivity check. Now, if you want to properly verify this, the number of scenarios are huge. Because, for instance, let's say you want to check a certain target IP, in this case IPC, and then you want to make sure the functionality that you are looking at works correctly, when the other IP is doing nothing, or one other IP has some operation going on before or after your target IP. And basically the number of combinations is huge. Now, the way they used to do this is through simulation. They used to write a number of tests. They used to adapt the test bench to check all these functional connectivity paths. Now, there was here, this is the interesting part of the presentation. And, well, we have these nice interface level assertions that come along with the IP. One of the challenges we often see is how can we exploit more, the verification done at the IP level, at the SoC level? Well, that is one way of doing this. So there is these assertions that are developed for the IP are reused at the SoC level to verify SoC level functional connectivity. I show you a bit more about this. This is just a scheme. For instance, you have an IP that is generating a request that goes through some connectivity IP that reach a destination, which could be the CPU, for instance. And we have these simple assertions, but at the interface level for all of these blocks. Now, the great idea is to kind of use this assertion that we saw. I go back to the assertion for a moment. I want to. So this is how the schematic assertion looks like. So the key point here is that you have a clear separation between the scenario you're looking at and what you're trying to prove. Okay, I am in this situation, I have a request, implies this is going to happen. So here, what we do is to recombine these parts of different assertions and build new assertions. So we reuse the IP level assertion, taking the portions of them and recombine to build a new assertions that is talking about SOC level functionality. And that is the great thing about this solution. And that's how you reuse IP level assertions to verify SOC level functionality. This is, for instance, an example of how this final assertion would look like, where you have taken bits from different IP level assertions. This specific one is talking about the interrupt controller, but they have done this also to check connectivity between master slaves across, the full address range, considering that a lot of other things can happen in parallel because, as you know, formal is exhaustive. Now, Renesas reports these results, and interesting results because in simulation they had about, for this specific case of the interrupt controller, they did the clear head-to-head comparison, and they had about 130,000 lines of test code that obviously part of it was automatically generated, and they had about 40 days of effort and 547 hours of runtime. And then looking at, let's say, one interrupt sources at the time, they had with formal much less lines of code generated, 12,000, and 4.5 days of effort. Obviously, this is not the effort to verify each and every IP fully. This is the effort to only, let's say, write the IP level assertion for interrupt interface, and then recombine these assertions. So this is a huge improvement. And then to do, in terms of runtime, we have 9 hours. Here, the runtime goes up to 80 hours when you verify all possible combination of interrupt sources at once. This is a big number, but still is much lower than the simulation one. And obviously, here you are doing an exhaustive verification that it's much, much higher quality of what you get into this number. So much less effort, less runtime, and much higher quality. Okay, so in summary, we have this, high coverage formal verification with this interface level property, operational property, and then this can be reused for different variation of the single IP. And then the key of the presentation is that this assertion can be leveraged to do SOC integration verification, and they can check, for instance, all combination of communication channels. We saw the examples of the interrupt controller, and we saw that our customer had about an order of magnitude of savings. And if you think this is just for the interrupt controller, then they apply this to other interconnectivity checks, plus all the variation of the products. This adds up to a lot of money savings. So I'm done. Any questions?
Thank you.
Does it sound interesting? By the way, you know, you don't need to wait 20 years to adopt this. It can be done today.
Or tomorrow, maybe.
So I was thinking, let's say we have another scenario where at a P level there is a standard random verification environment. There's a nice IP that they're happy to verify with the normal UVM approach. Does it seem to me that maybe you can still use this approach like the system chip team just decided I want to use formal and then just need to write the IP block of formal looking just over from all like using exactly the same approach but directly from a system and chip level even without the IP formal property developed before.
Sure, you can do that. Yeah. I mean, obviously here the advantage is that you use this for IP level verification and also the SOC.
Yeah, but more like, because maybe sometime IP was already verified, they're happy, they don't want to do the job informal, but still in system chip level they are a bit concerned about all the, maybe there are 20 of this IP, so the combination is too much.
Yeah, that is correct also because you do not need to do some kind of complete verification of your IP. You can just write the assertion for the specific interface you want to leverage at SOC.
I have a few questions. So you showed the timing diagram. You had a slide and you said you could extract properties. Is it true that you could automatically extract properties from timing diagrams?
No, I didn't say automatically.
Okay, fine.
No, not automatically. It's, well, that if it would be automatically, then I probably would be sitting here with bags of money.
Well, you could now go and do this and make money, right? So
I mean, it's a very, easiest way at the moment that we find to translate timing diagrams into assertions using this clear separation of assumption and commitments.
Okay. So I have two other questions. Yeah. One is regarding constraints. So the biggest challenge in adoption of formal is you have massive number of constraints and we don't really know whether or not we have conflicting constraints. And do you have a solution for this? Do you have ideas on how this could be resolved? And as a second question, if I may add, if we could do this later, Mike and the panel, is coverage and completeness. Coverage and completeness. I would like to know what your thoughts are on that.
Okay, so I'm happy to answer this. They are not targeting actually this specific presentation.
So we take that as the first question for the EDA panel?
Sorry?
Should we take that as the first question for the EDA panel?
So your question was it possible to generate properties from waveform? The answer is absolutely yes. As a matter of fact, there's more than one, I'm not going to plug names, more than one commercial tools available today, automatic property synthesis from the RTL. If you extract the waveform, either from PDF or from FSDB or from VCD, the waveform themselves, together with the RTL, could be the basis for automatic property synthesis. Absolutely. I'll be happy to talk to anybody after that.
Okay. That's okay. That's okay. Okay, thanks, Sergio.
Thank you.